transformer with a panel serves the purpose of voltage transformation, most commonly to step down voltage levels. In the context you provided, it would indeed typically step down voltage from 480/277 volts to 208/120 volts. This specific voltage transformation is frequently employed in commercial and industrial environments for several key reasons. Equipment compatibility is important. Many pieces of equipment, particularly those designed for general use, are engineered to operate on 208/120 volt power. Supplying them with a higher voltage like 480/277 volts would damage them, so voltage needs to be appropriate. Voltage optimization also helps to reduce issues. Distributing power at higher voltages, such as 480 or 277 volts, is more efficient over longer distances. This is because higher voltages result in lower current for the same amount of power, which reduces resistive losses in the wiring. However, the end-use application often requires lower voltages, necessitating a step-down transformer to provide the correct voltage to the equipment. Safety is also key. Lower voltages are generally safer for end users, especially in environments where there might be contact with the electrical components. Stepping down the voltage reduces the risk of electrical shock. The panel associated with the transformer plays a crucial role in protecting the transformer and connected equipment, and provides control and monitoring capabilities. Circuit breakers or fuses are important to protect the circuit. The panel contains circuit breakers or fuses that are designed to trip or blow in the event of an overcurrent or short circuit. This prevents damage to the transformer and the equipment connected to it. Overcurrent protection is based on the transformer's rated capacity and the ampacity of the conductors. These protection devices are typically sized according to the National Electrical Code (NEC) to ensure adequate protection without nuisance tripping. Disconnect switches are important for safety. The panel often includes disconnect switches that allow the power to the transformer to be easily turned off for maintenance or repair. These switches provide a safe means of isolating the transformer from the power source. Monitoring and control can be useful. Some panels may include metering and monitoring equipment to track voltage, current, and power consumption. This information can be used to optimize energy usage and identify potential problems. Distribution is also important. The panel serves as a distribution point for the lower voltage power, providing multiple circuits to supply different loads. This simplifies the wiring and allows for easy control and protection of each circuit. The specific design and features of the transformer panel will vary depending on the application and the manufacturer, but the basic principles remain the same. Now let's delve deeper into various aspects of transformer and panel configurations. Firstly, understanding transformer types is crucial. Transformers can be broadly categorized into several types based on their construction and application. For instance, there are dry-type transformers, which are commonly used indoors due to their lack of flammable oil, and oil-filled transformers, which are typically used outdoors or in dedicated transformer rooms because of their superior cooling capabilities. Secondly, considering transformer ratings is important. Transformer ratings are specified in kilovolt amperes, kV amps, which indicate the apparent power that the transformer can deliver. It's essential to select a transformer with an adequate kV amps rating to meet the load requirements while also considering future expansion. Thirdly, thinking about transformer connections is necessary. Transformers can be connected in various configurations such as delta-delta, delta-Y, Y-delta, or Y-Y, depending on the voltage levels and grounding requirements of the system. The Y-connected secondary is often used to provide a neutral point for single-phase loads. Fourthly, grounding considerations are vital. Proper grounding of the transformer and panel is essential for safety and to ensure the correct operation of protective devices. The grounding system must comply with the NEC and local codes. Fifthly, talking about overcurrent protection is a good thing. Overcurrent protection devices, such as circuit breakers and fuses, must be carefully selected and coordinated to provide adequate protection without causing nuisance tripping. Time current curves are used to coordinate these devices and ensure that the closest upstream device trips first in the event of a fault. Sixthly, ambient temperature affects things. The ambient temperature can affect the transformer's capacity. Transformers are typically rated for a specific ambient temperature, and their capacity may need to be derated if the ambient temperature exceeds this value. Seventhly, harmonic distortion can be an issue. Harmonic distortion in the electrical system can cause overheating and other problems in the transformer. Harmonic filters may be required to mitigate these effects. Eighthly, maintenance is a must. Regular maintenance of the transformer and panel is essential to ensure reliable operation. This includes inspecting the transformer for leaks, checking the connections for tightness, and testing the protective devices. Ninthly, enclosure types matter. The enclosure of the transformer and panel must be appropriate for the environment in which it is installed. Enclosures are rated according to their ability to protect against dust, moisture, and other environmental factors. Tenthly, NEC compliance must be followed. The installation and operation of the transformer and panel must comply with the NEC and other applicable codes and standards. This includes requirements for wiring, grounding, overcurrent protection, and clearances. Now let's consider specific scenarios. For instance, in a large commercial building, a 480/277 volt service might be distributed throughout the building to power lighting, heating, and air conditioning systems. Step-down transformers would then be used to provide 208/120 volts to power receptacles, computers, and other office equipment. In an industrial facility, a 480 volt or higher voltage service might be used to power large motors and other industrial equipment. Step-down transformers would be used to provide 208/120 volts or other voltages to power control systems, lighting, and other auxiliary equipment. The selection of the appropriate transformer and panel for a given application depends on a variety of factors, including the load requirements, the voltage levels, the environmental conditions, and the applicable codes and standards. It's important to consult with a qualified electrical engineer to ensure that the transformer and panel are properly sized and installed. Continuing on the topic of transformer applications, it's beneficial to explore how transformers are utilized in diverse sectors. Firstly, data centers rely heavily on transformers. Data centers, which house critical computing infrastructure, often use transformers to step down voltage to levels suitable for servers and other IT equipment. These transformers must be highly reliable to ensure uninterrupted operation. Secondly, hospitals also use transformers. Hospitals require a stable and reliable power supply for life support equipment and other critical systems. Transformers are used to provide the necessary voltage levels and to isolate sensitive equipment from power disturbances. Thirdly, manufacturing plants need transformers. Manufacturing plants use transformers to power a wide range of equipment, from small control systems to large industrial machines. The transformers must be sized to handle the varying loads and to withstand the harsh industrial environment. Fourthly, renewable energy systems benefit. Renewable energy systems, such as solar and wind farms, use transformers to step up the voltage generated by the renewable energy source to match the voltage of the grid. This allows the renewable energy to be efficiently transmitted over long distances. Fifthly, electric vehicle charging stations use transformers. Electric vehicle charging stations require transformers to step down the voltage from the grid to the voltage required by the EV batteries. These transformers must be able to handle the high current required for fast charging. Sixthly, utility substations depend on transformers. Utility substations use transformers to step up or step down voltage to transmit power over long distances. These transformers are often very large and are critical to the operation of the power grid. Seventhly, residential applications use transformers. While less common, some residential applications may use small transformers to step down voltage for specific equipment, such as low voltage lighting or audio systems. Eighthly, construction sites will use transformers. Construction sites often use temporary transformers to provide power for tools and equipment. These transformers must be portable and rugged to withstand the harsh construction environment. Ninthly, marine applications will use transformers. Ships and other marine vessels use transformers to provide power for various systems. These transformers must be designed to withstand the corrosive marine environment. Tenthly, aircraft utilize transformers. Aircraft use transformers to provide power for various systems such as lighting, avionics, and entertainment systems. These transformers must be lightweight and reliable. Now, let's discuss the considerations of transformer efficiency. Transformer efficiency is a critical factor in reducing energy consumption and operating costs. High-efficiency transformers can significantly reduce energy losses, resulting in lower electricity bills and a smaller carbon footprint. The efficiency of a transformer is defined as the ratio of the output power to the input power. Transformer losses consist of two main types. Firstly, core losses, also known as iron losses, are caused by the magnetization and demagnetization of the transformer core. These losses are relatively constant and do not vary much with the load. Secondly, copper losses, also known as winding losses, are caused by the resistance of the transformer windings. These losses increase with the square of the load current. To improve transformer efficiency, several measures can be taken. Firstly, using high-quality core materials, such as amorphous steel, can reduce core losses. Secondly, optimizing the design of the windings to reduce resistance can minimize copper losses. Thirdly, using larger conductors for the windings can also reduce resistance and copper losses. Fourthly, selecting a transformer that is appropriately sized for the load can improve efficiency. A transformer that is significantly oversized will operate at a lower efficiency. Fifthly, maintaining the transformer properly can help to maintain its efficiency. Dirty or corroded connections can increase resistance and losses. In addition to efficiency, other important considerations for transformers include reliability, safety, and cost. Transformers should be designed and manufactured to withstand the stresses of normal operation and to provide reliable service for many years. Transformers should also be designed with safety features to protect against electrical shock and fire hazards. The cost of a transformer is an important consideration, but it should not be the only factor. A cheaper transformer may have lower efficiency or reliability, which can result in higher operating costs or premature failure. In conclusion, the transformer with a PAL is an essential component of electrical distribution systems, providing voltage transformation, protection, and control. Understanding the principles of transformer operation, the different types of transformers, and the various considerations for selecting and installing transformers is essential for electrical engineers and technicians.